Thank you everyone for coming today, and thanks USENIX for inviting me. I'm indeed Kostya Serebryany from Google, and my talk is about OSS-Fuzz, which is a fuzzing service for open source. I will start with a little bit of fuzzing-related archaeology, proceed with a demo of a tool called libFuzzer, a tool used for fuzzing mostly C++ and C applications. And I will then proceed to describing the service. OSS-Fuzz, a continuous fuzzing service. So first of all, how many of you know what fuzzing is? Raise your hands, please. Yeah, this is a security conference. For those who don't know, if you test your application, you essentially pass a fixed number of fixed inputs to your API. If you fuzz your code, you have an infinite loop where you generate somehow inputs for your API and feed these inputs into your API. There are lots of different ways of fuzzing, and I will be only talking today about what is usually called coverage-guided fuzzing. The idea of coverage-guided fuzzing is very simple, all on the slide. You initially need to acquire a set of inputs for your API. We call it seed corpus. And then in infinite loop, you pick an input from the corpus, you apply random mutation to that input, you feed the new mutation, the new mutated input into your API, and you look at the coverage that was obtained by running this input. If you see any new coverage, it means that the input is interesting and you add it back to the initial corpus. And then you repeat. The idea is not new. The tools and the papers describing coverage-guided fuzzing started appearing at least a decade ago. Google started using something like this at least in 2013. We had an internal tool which we used to fuzz lots of different software, including FFmpeg. You can find an amazing blog post about 1,000 bugs in FFmpeg, and we found a few hundred more afterwards. Approximately at the same time, late 2013, AFL has been released. Who knows AFL? American Fuzzy Lob is probably one of the most popular coverage-guided fuzzing engines nowadays. It's developed by my colleague Michal Zalewski at Google. About a year ago, my team has released libFuzzer, yet another fuzzing engine. And I will talk in more detail about this fuzzing engine. Yet, we had Heartbleed. Who remembers Heartbleed? Security conference. So the bug was introduced into OpenSSL in late 2011. In fact, it was December 31st, 2011, which is a fun by itself. And for over 2 years, this version of OpenSSL was vulnerable, and the industry still doesn't know how many times and where it has been exploited. This was a buffer overflow causing an information leak so that an attacker from a remote server could gain access to all the process memory from your service. In March 2014, this bug has been discovered by 2 independent groups. One from Google using code audit, basically reading the code. And the other by Codenomicon by highly specialized generation-based fuzzer. Both approaches are extremely expensive. This is probably one of the reasons why the bug was found only 2 years later. A year after the Heartbleed was made public, Hanno Böck, a security researcher from Germany, demonstrated how to find Heartbleed using AFL in 6 hours. I took his code, simplified a little bit, and 2 days later demonstrated that libFuzzer can find Heartbleed in 10 seconds. And this lovely animated GIF here actually shows how libFuzzer finds Heartbleed. It is indeed a heap buffer overflow. The difference between times for AFL and libFuzzer is not in the algorithm, but in the fact that AFL at that time was out of process, so it was launching separate processes for every run, and libFuzzer wasn't. So one important question that I think everyone in security community and most people in open source community should ask themselves and know the answer. Why did Heartbleed exist for 2 years? Maybe our OpenSSL team was not well funded. Could be. Maybe the fuzzing tools were not widely available. That's most likely true, but they were available. But the main reason, I think, for this is that fuzzing was done by security researchers, not by the code owners. As many security researchers as I can see here, this is not enough to find bugs in all of the source software, not even in all open source software. Another interesting question, maybe even more interesting. Why didn't OpenSSL team fuzz until 2016? Maybe not because it was not well funded. Probably could be because the fuzzing tools, though existed, were not widely known, or maybe they were poorly documented or something else. But my main answer is because there was no infrastructure to run fuzzing continuously and in automated fashion. And so we started asking these questions to each other. And in 2015, we implemented a service. In fact, it was a 100-line bash script. We ran this bash script on 6 different 8-core VMs, testing 6 different open source projects. And we found multiple bugs in all of those projects. The project owners fixed those bugs, and we received feedback, which made us want to scale it up. So December last year, we launched publicly a service called OSS-Fuzz. It is a continued automated fuzzing that uses Google's virtual machines and Google's infrastructure. Today, it uses both libFuzzer and AFL as fuzzing engines, and we expect to add more fuzzing engines in future. It also uses the sanitizers together with the fuzzing engines to actually find bugs. Who knows what the sanitizers are? Address sanitizer and security conference. Come on, address sanitizer. I will cover it a little bit later. The service is available for free for important open source projects. And we deliberately don't define what important is. So this is open to your interpretation. Basically, if you think that a given open source project is important, it most likely is. We didn't build this service from scratch. Instead, we reused the same infrastructure that we have been using to fuzz test components of the Google Chromium since 2015. And that infrastructure has found several thousands of bugs in the Chromium source code. Before I proceed with OSS-Fuzz details, I want to show you how libFuzzer works. So this is the simplest possible example of an API that you want to test. The first function, fuzzMe, suppose this is an API in your application that you want to test with fuzzing. Who can spot the bug, by the way? The string is not zero terminated. Well, this is not a string. This is an array of bytes. And the type is actually unsigned int. Who else have a guess? Thank you, correct. So the API assumes, well, this is not written in a contract, but you usually think that if you have data and data size, then data size is actual size of this array data. And if data size is 3, the first 3 characters are F, U, and Z, then the code will access an array element with index 3, which is out of bounds. But this test is very hard to, this bug is very hard to spot with testing because you have to know the specific input that triggers the bug. But for fuzzing, it's very simple. The second function on this slide we call it a fuzz target. This is a function with C linkage, so you can use the tooling with any language that can link against C. This function has a specific name and it has a specific signature. Basically, you pass an array of bytes with its size to this API function. And inside this function, inside this fuzz target, you feed the data into the API in question. That's it. Now, if you want to use libFuzzer, all you need is to build your code with a special flag and run it. The special flag, and this flag is actually implemented only in the very, very fresh Clang compiler. fsanitize equals address, comma, fuzzer. Address stands for address sanitizer, a tool that detects heap buffer overflows and heap use after freeze and some such. You can use another sanitizer with libFuzzer. And comma fuzzer means that at compile time, you add coverage instrumentation suitable for fuzzing, and at link time, you link proper libraries. A little bit details about what is a good fuzz target. So again, fuzz target is a function with a specific signature that passes the data and size to the API in question. The fuzz target should be a function that consumes any data. By that I mean that if the function aborts, exits, crashes, asserts, times out, or goes out of memory, it should be considered a bug and should be fixed. It should be single process. It cannot spawn any other processes. At least we won't be able to go through into other processes. Ideally, it should be deterministic. Ideally, it shouldn't touch any global state. And the smaller the piece of code it touches, the better. The efficiency of fuzzing is actually very sensitive to the amount of code you are trying to fuzz. So now I'm going to switch to a demo. There is a site called tutorial.libfuzzer.info, which in fact just an alias for a GitHub page, where we have a self-guided tutorial for libFuzzer. You can download a Docker image, or you can download all the needed software on your Linux box, and you can run the commands and see how it works. I will only show you a few command lines. I will not show you how to build stuff. It's all on the tutorial. So we will start with the Heartbleed, and I will demonstrate my claim that Heartbleed can be found in a few seconds. So here we have a directory which contains a pre-built binary of the fuzzer. And let us look at the code. So I'm not an expert in OpenSSL API. I took this code from Hanno Böck 2 years ago. I don't know what it does. All I know is that it takes data and the size and passes it to the OpenSSL API. And if you know what a OpenSSL API does, you probably understand what is written here. This is all you need to implement in order to find Heartbleed. So the usual way to run libFuzzer is to create a directory. I call it Corpus. Then put initial input samples into that directory. And then run the fuzzer binary like this. The fuzzer binary name and the Corpus directory. The OpenSSL Heartbleed bug is interesting in a certain way. It is so shallow, it is so easy to find that you don't really need to put any samples in your corpus. But let us see. So I'm running the binary, and the most interesting part here is this fourth column, which says cov, colon, and the number. So this number, sorry, it was too fast. So this column indicates how many parts of code we have discovered so far. Well, technically these are edges in the control flow graph, but you can just think of them as lines of code if you wish. So as you can see, this number grows over time, and eventually we hit the bug. And for those who don't know what address sanitizer is, here is basically all you need to know about address sanitizer. Address sanitizer is a tool that finds heap buffer overflows and other kinds of memory bugs at runtime. In this case, it found a heap buffer overflow. We're reading 33,000 bytes, and the second frame of the bug report is something Heartbeat. This is why the bug was called Heartbleed. Let's look at the output after the bug is reported. The last line here says test unit written to crash and then sh1 sum. What does it mean? It means that now we have a file called crash sh something. Let's look at it. Some binary data, and by the way, the file is unusually small. These are the bytes that you need to put into the fuzz target to trigger the bug. And so, all you need to do now is to invoke the fuzzer binary with the parameter file name instead of the directory name. And instead of fuzzing, it will just reproduce the bug. So you can debug it, you can fix and verify that you have fixed it, and so on. Let's look what is going on in the corpus. So remember, I created an empty directory. Now this directory is not empty. The fuzzer has found a number of inputs that have triggered new coverage, and all of those inputs were saved in the directory. Now you can use these files to unit test OpenSSL. You can also now run the fuzzer with the same corpus, and I hope it will find the bug sooner. Yeah, you've seen it. It found the bug quicker than on the first step, because now you already have the initial seed corpus, which is, in terms of search, it is closer to the bug than no corpus. Let me show you something else. So WOFF2 WOF is a library for rendering web fonts. It is used at least in Chrome, but probably in some other browsers as well. And in order to fuzz this library, you need to implement quite a bit of code. Here it is. So again, this is a fuzz target. It takes data and size as parameters, and it passes data and size into the API we want to fuzz. This is it. Let us create a directory called corpus, and let us run the fuzzer on this corpus. As you can see, the coverage grows slowly, but it's pretty low. It's in less than 100. Eventually, it will grow up. It did. But we're impatient. We want the coverage to go faster. Luckily, for WOF library, we also have seed corpus, which is the fonts in this data format. Let's find them. Yep, we have a directory here, which is conveniently called seed corpus, which has some files of the required data format. And now, if we want to use this seed corpus, we just pass it as a second parameter to the fuzzer binary. You could pass third parameter and so on. You can use any number of directories with libFuzzer. The first directory is Readwrite, so new samples will be stored in the first directory. All other directories are used at the initialization state only and are read only. So you can see that the coverage is initially much higher, and it also grows much quicker because we gave a fuzzer something to start with. WOF is not that easy to find bug in compared to OpenSSL Heartbleed. So we may want to scale our bug finding a little bit by using multiple CPUs. The machine I'm running on is a virtual machine with 8 cores, so why not use all 8 cores? And we have 2 flags with libFuzzer. one flag tells how many jobs to run in total. Another flag tells how many jobs to run at the same time. And this will look like this. Time to switch to another terminal. And we can look at the logs. So you can see that the coverage grows, this fourth column. And some of the lines say reload. It means that the fuzzing processes, I've launched 8 of them, cooperate with each other. If one process finds anything interesting, an input that triggers new coverage, it creates a file on disk in the first directory called Corpus with that input. All other 7 processes detect that a new file was added, load it, run it, and if they also find it interesting, they keep it for themselves. And so all 8 processes cooperate. Fuzzing is good in the sense that it scales almost infinitely. And on our service, which I'm going to talk later, we don't use multiple processes on a single machine. We use a cluster. And we exchange files using a network system. And here it is. It actually, no? It did find the bug. Let me try to show it to you. I'm bad at typing. Okay. So one of the instances found a bug. The other instances continue running, trying to find maybe some other bugs. So in this case, this is also a heap buffer overflow. And it's a nice one. It's a write of just 12,000 bytes out of bounds. Let me demonstrate you one last thing. No, not here. Who knows what libXML is? Yeah, libXML is a library for parsing XML language. It has been pretty buggy until recently. It's probably still somewhat buggy, but it is becoming harder to find bugs in it. We reported probably 100 bugs to libXML over the few years. And here is a fuzzer. Actually, let me show it to you first. I'm sorry, it doesn't want to quit. Yep. So libXML fuzzer is a very time-consuming thing to implement. Here it is. Again, you have a fuzz target, and you pass the data into the API you want to test. That's all. Let's run it again. As you can see, the coverage grows. You need to look at the 4th column. Now the coverage is already 1,100 plus. But there is one more improvement that we can make, at least for targets of this kind. This improvement is called fuzzing dictionaries. You can actually tell a fuzzer that you are dealing with an input language that, oh, I don't have Vim. Yeah. So you can tell the fuzzer that the input language deals with certain sequences of bytes. And you give the fuzzer these sequences of bytes as a way to simplify the work for it. Okay, so how do we run it? We run it like this. And I hope you can notice on the screen that the coverage is already much higher and it grows faster. So coverage dictionaries are useful things for many input types. Okay, we're short of time. I'm switching back to the presentation, and I will now continue talking about the OSS-Fuzz service. As I mentioned, we launched the service in December 2016, less than a year ago. And since then, we have reported over 2,000 bugs. And this colorful pie chart tells you the demographics for the bugs. As you can see, about a quarter of the bugs are what we usually call security bugs in C++. Buffer overflows on heap globals and stack, use of the freeze, uses of uninitialized memory. Another large class of bugs, they may or may not be treated as security depending on your attack scenario. Out of memory, timeouts, stack overflows, assertion failures, null dereferences, all kinds of other crashes. If you care about DDoS attacks, these are security bugs as well. And finally, we have the largest single section, which is labeled UBSAN. UBSAN stands for Undefined Behavior Sanitizer. This is a tool that finds lots of different misbehavings in C++. These are most usually signed integer overflows and shifts by invalid amount in C and C++. Most of them are just correctness bugs, not security, but occasionally a signed integer overflow is actually a security bug as well. Some of you might have heard war stories about signed integer overflows in security context. The bugs were reported to over 60 open source projects, and the chart here shows the top 30. The top several, we reported many hundreds of bugs to the top few projects. It can be reasonably explained. Projects like FFmpeg and LibreOffice, first of all, they're huge. Second, they're old. And third, they deal with a lot of very complex data types. So there is no surprise that we found so many bugs there. But the long tail is also interesting. You may notice OpenSSL at the bottom of this top 30. And that is also around a dozen bugs. We have been reporting OpenSSL bugs to them for a few months until the flow has ended. And the OpenSSL was actually very good at fixing them. I would actually say more. OpenSSL team did a lot to improve their own fuzzing, and so the last of those bugs are the results of the OpenSSL team making changes in their code base and their testing harness to actually make fuzzing more efficient. I want to stop on one other project, Wireshark. Who knows Wireshark? Wow, security conference. I don't know much about Wireshark. Probably you know much more about me, but as far as I understand, this is some kind of network packet inspection tool. And you will tell me more precisely, I hope. And the demographics is more or less usual. We see the usual suspects like buffer overflows, we see timeouts, leaks, out of memories, and we see lots of bad shifts and signed integer overflows. But what makes, for me, this project special is the discussion on the project mailing list about the bugs. They say, heap buffer overflows, okay, we'll fix them. Stack overflows, yeah. Timeouts, oh my god, timeouts are severe. They cause denial of service due to infinite loops. This is true, but this is something that many code owners don't understand. Timeouts and out of memories and leaks are equally bad bugs for security and for stability, but they are awful for fuzzing. Anything that causes the fuzzer to time out means that you cannot fuzz forward. And the fact that we found 50 bugs in Wireshark, this is because the Wireshark team has fixed promptly the early timeout bugs that we've posted, and so the fuzzers were able to go deeper. On OSS-Fuzz page, we have a document called Ideal Integration with OSS-Fuzz. In fact, this is our vision of ideal integration of fuzzing, not necessarily with OSS-Fuzz, with some open source project. So what we want project owners to do? First of all, we want the project owners to maintain their own fuzz targets in their revision control. fuzz target, fuzzing harness, whatever you call it, is not a separate thing. It should be a part of your code repository. It should be built with the rest of the code, at least with the tests, to avoid the bit rot. The fuzz target has to have a good seed corpus, which provides good code coverage. And the most important is that the project has continuous testing for the fuzz target with this seed corpus, preferably with the sanitizers. I don't say that they have to fuzz continuously. That is welcome, but this is not necessary. We want them to test the fuzz target with the seed corpus as a regression test. This way, we will make sure that the code in the fuzz target is always up to date. And it's also a very good regression test. We also want to have all the fuzz targets free of timeouts and out of memories. Basically, these bugs should be treated as significantly as any other kind of crashes because they hurt fuzzing and because they're bad for security. And where applicable, we ask code owners to provide fuzzing dictionaries. A few words about life of a bug. So what happens when one of our virtual machines finds a bug in a given project? First of all, we try to deduplicate it against any known bugs. We don't want to file many duplicates. We usually manage to avoid filing duplicates. Then we try to minimize the reproducer. It is much nicer to deal with several bytes of input than with several kilobytes of input. And we also try to find the regression range. In many cases, the bugs we find are not old bugs that we have just discovered, but the newly introduced bugs. And then for developers, it is convenient to know where the bug was introduced. Then a private issue is reported, and the code owners are CC'd. We use the same bug tracking system that Chromium developers use, and that system actually has the private flag. So the code owners see the bug, and no one else does. Then, hopefully, owners fix the bug. And we encourage the owners to extend their seed corpus with the reproducer that triggered the bug so that they have it as a regression test and they have it for future fuzzing integration as a seed. Then we rebuild the fuzz target. We do it every 24 hours. And if the bug is fixed, we try to identify the revision range that fixed the bug, which is also convenient, and we automatically close the bug. No humans are involved in this step. The bugs are made public either in 30 days after the fix or 90 days after we reported the bug, whichever is earlier. This is an example of a bug report. Basically, this bug report gives you everything you need to reproduce the bug. It has a link to the input that reproduces the bug. It has the regression range. It has a summary of the bug report. In this case, it's again heap buffer overflow. I'm sorry. The code owners are CC'd, and there is a link to a much more detailed dashboard with the bug details. I'll skip this one. One of very important bits about fuzzing is code coverage. You really want to maximize code coverage for your fuzzers. And we provide a somewhat simplistic dashboard for code coverage. You may also use your own coverage tools if you prefer. But we encourage everyone to look at the code coverage dashboard and see why some of the code is not covered. Most often this is because this code cannot be executed with the given API, so we need more fuzz targets. Sometimes it is beneficial to add more elements to the seed corpus. How to participate in OSS-Fuzz? First of all, your project has to be an important OSS project, and I already explained what I mean by important. Then please send us pull request. All we need from you is 3 tiny config files. First config file gives the URL for your project and a list of emails for the code owners so that we can file bugs against you privately. The second file, Docker file, is a built environment Like you install the dependencies and you pull your code basically. And the third file is build.sh. It tells us how to build your source. Unfortunately, open source code doesn't have a unified build system. We have over 80 projects right now. All of them have different build systems, 80 different build systems. So we have to delegate building to you. I will share the slides with USENIX, and you will be able to click on the links if you want to. And then once these files are submitted, we'll start fuzzing your project, and we'll need the help to improve fuzzing over time. First of all, fix the bugs, including timeouts and out of memory, please. And second, monitor coverage and help the service to find more coverage by providing more seeds, by enhancing the fuzz targets, and whatever else you can see there. Google actually rewards for doing this. This is not just free service. We pay money to open source code owners to participate. We pay $1,000 for the initial integration and up to $20,000 for what we call ideal integration. Why we are doing this? First of all, Google itself depends on a huge number of open source projects. And if the project owners improve their own code, it improves the Google security. So we win. Even if Google doesn't use a particular open source project, Google's users use it, or some other users on the internet use it. And so by making those projects more secure, we make internet more secure. We also win. And finally, we need to popularize continuous fuzzing among open source and not open source developers. It is still not well-known technique, unfortunately. Almost 15 years ago, Kent Beck declared and started advertising what is called test-driven development. Who knows what test-driven development is? Good. So this is a very good technique. I wish everyone used it, but it is drastically not sufficient for security. Remember, testing doesn't give you security at all. Fuzzing may give you some security. Testing doesn't at all. So in 2017, I proclaimed fuzz-driven development. By that I mean that every API that you develop, maybe even that you maintain, should be a fuzz target, something that is easy to fuzz. Tests for the APIs should be the same as seed corpus for fuzzing. And the projects need to have continuous integration that include continuous fuzzing. They may have their own continuous fuzzing, or they may use services like OSS-Fuzz. And this is not limited to C or C++, which are memory unsafe languages. Very similar approaches are now being adopted by the Rust community and by the Go community. And so the rest should, I believe, should also follow. So I'm wrapping up. First of all, I hope I convinced you, and I hope you will convince everyone else around you, that coverage-guided fuzzing is now very, very, very simple. There is basically no reason not to do it anymore. Second, I believe that fuzzing must be done continuously and in automated fashion. There is no excuse for doing fuzzing once and then dropping the ball. And the fuzzing harness in a given project should be maintained by code owners. And finally, there is a service called OSS-Fuzz. It's a public fuzzing service for open source. Our goal is to make common software infrastructure more secure by applying modern fuzzing techniques at large scale. Since December 2016, we found over 2,000 bugs in open source projects, and most of them were fixed. I don't want to stand between you and lunch, but questions are welcome. Thank you for your attention.
Any questions, please feel free to come up to the mics in the aisle.
Hello. Thank you for your talk. So we saw that OSSFuzz had revealed lots and lots of bugs across many different libraries. So I was wondering if this could be attributed to some sort of technical features that it had that were different from other code coverage guided fuzzers, or do you think it was mainly the fact that you integrated it to the pipeline that made it better?
is there any difference between public tools and what we have? No, there is no difference because all the tools we use on OSS-Fuzz are public anyway. And I believe that the success is the scale and the integration, exactly as you say. Maybe there is a little bit of secret sauce in this thing that scales runs, but not much.
Okay, thank you.
Hi, Kostya. Great talk. I just had a clarifying question. So I'm trying to reconcile in my head. What I heard was that Google is trying to encourage more fuzz testing for open source.
Correct.
And that was the message. But then there were a whole bunch of other efforts, and I didn't understand whether they were at Google or elsewhere for other languages. So there seems to be something about, there is a constraint in your talk about the languages you're actually encouraging to. Is this aimed at C and C++, or is it aimed at all open source projects, even those written in languages other than C and C++?
Do we want to support or do we support other languages? So currently we're kind of C and C++ centric, but this is for historical reasons. The tools that we have work with any language that can be compiled with LLVM, and that, for example, includes Rust. libFuzzer works with Rust, and I wish to have Rust libraries on OSS-Fuzz. I don't have right now. I hope to have them in the future. As to any other languages, we don't really have support for anything that doesn't compile with LLVM yet, but there will be demand, there will be implementation.
Okay, thank you.
Hi. So thanks for the presentation. It's in the same line. So in your opinion, how much work would we need to have the same library for other languages, let's say Python, or that are not LLVM based?
The library, the existing library could be reused for a given language without any modifications. The only thing you need is you need to implement the coverage instrumentation for your toolchain, for your compiler. And just to give you a feeling, the implementation is in GCC, if you want to use the GCC compiler, is roughly 50 lines of code. So if you can modify your toolchain, it's not a big deal, but you have to do it.
Let's take one more question, and then I'll encourage you to stick around and ask more.
This is a quick question. You say that you retrieve a Heartbleed in OpenSSL within 10 seconds, right? I was wondering, what's the coverage of the fuzzing you're performing to have the result in 10 seconds? Are you fuzzing all OpenSSL or just the one function?
Good question. Let me just show it to you. So this is the OpenSSL GitHub. This is not my repository. And this is the directory called fuzz. And this is the fuzzers they have. So it's about 10 different APIs that they have on their GitHub. And we fuzz all of those in OSS-Fuzz. Does it cover all of the code? Oh God, no. It doesn't cover even half of OpenSSL. But it's more than one function. Much more.
So it's not driven to retrieve specifically Heartbleed. It was a more general fuzzing.
Yes, this is more. Well, every fuzz target tests a specific function, but we have many fuzz targets.
Okay, thank you.
Okay, please enjoy your lunch. Let's thank both the speakers again.